thank you all very much for joining this webinar. And when Pan asked me to give this talk, I was debating what to talk about it, but at the end I decided on talking about something that I don't know very well. That's detonation. As many of you know, I'm a physical chemist by training. Got into detonation rather fortuitously. So what I want to say is that I'm by no means an expert in the area. Rather, I just wanted to talk to you my learning notes from my recent involvement. And there are a lot more people in this field at this time and before me who understand this problem, whether it's from historical context or from scientific context, far more than I do. But that said, I still would very much like to talk to you about what I learned over the past few years and share with you some of the thoughts. Many of the things I'm going to talk about is by no means final, as many things are work in progress. And also I wanted to acknowledge many of the contributors. In fact, many of the ideas, or almost all of the ideas are not mine, come from my discussion with various people in the field. This includes Andrea Kempf from Duisburg. And he is the one who inspired me to think about the detonation in a way that that was a very interesting learning experience, to say the least, for me. And we relied on his code, in fact, and also the computer code by Alexei Prudnenko. And they provided so much numerical capability for us to learn what detonation is about. The work also involves Xingyu Zhao and her student Patrick Meager, who is visiting in my lab. Some of the experimental ideas came from Karim Ahmed at the UCF, and of course, my ex-student postdoc, Jackson Crane, now at the Queen's University, and Shen Si at the UCI, who did most of the work. So what I wanted to do is perhaps address the question here that if I were to teach, in the past, when I teach combustion class, I realized that the part that I had most difficulty was to teach detonation, as a matter of fact. And the disconnect in my mind is what's basically led to our current study. So for this talk, I wanted to go over some of the very basics about the origins of gaseous detonation, starting from 1D description that you can find in Professor Ed Law's textbook as a starting point. And going further, also in standard textbook, detonation waves have structures or cells. And then from that point, I wanted to move on to a topic that interested me for a few years, is what do smoke foil and the cell structure and size measured by smoke foil tell us? And I want to offer some perspective there. I want to focus on the death and birth of a cell, and particularly I wanted to look into the energy and momentum transfer in the overdriven wave as origin of those new cells. I want to talk about a feedback mechanism that's responsible for regular cell structure. Sometimes we call them stable detonation, but I will elaborate on the meaning of stable versus regular a little later. I'll give some speculation about the irregular cell structures, what's responsible for it, what's causing it. And lastly, more importantly, I wanted to perhaps convince the audience that a detonation is to us is a new opportunity, and I have my own perspective, perhaps take this opportunity to share with you. All right, so it's not a big group joining the webinar today, so feel free to jump in if you have any questions. And we, I didn't prepare an hour-long slides that I can talk perhaps for an hour long. So feel free to jump in anytime if there's certain points that's not clear to you. Starting from the 1D or 0D gaseous detonation description for reactants divided by an interface near which the energy is released, producing combustion products. We know that the 1D analysis leads to two branches. One is a deflagration branch, the other is detonation. So this 1D description is everything that we learned in graduate school, and in terms of energy, momentum, and conservation, continuity, those are pretty straightforward. However, if you look further into the structure of detonation, in the CND limit, or CND descriptions, Dulwich, von Neumann, and Doreen description, the internal structure of a detonation is that the initiation is done through a shock wave, followed by a reaction, therefore a rise in temperature. And then it is this coupling between shock and reaction heat release that sustains the detonation wave. And it shall release heat so fast in the burned gas such that the energy has nowhere to go but to choke the flow behind the detonation front. That choking condition was responsible for continued detonation wave propagation. Of course, detonation wave is impacted by chemistry, and therefore there are heat release structures in the ZND description. For example, as was shown here, a key quantity that I want to draw your attention to is behind the wavefront to the point of heat release. There's a period of time we call induction time in 1D detonation descriptions. Turns out this, because it's 1D description, and this induction time is very much related to the chemistry of the unburned mixture. And chemistry impact detonation mixture properties, Cp to Cv ratio, specific heat ratio, and among other properties at any level impacts the detonation. Now, of course, things are not that simple. 1D detonation in reality never exists. Detonation waves are always characterized by cellular structure. And this is a beautiful image in Yang Li's book showing how the shock waves are generated or propagated and bifurcated and so on. So, but this cellular structure of a detonation has been recognized for a very long time. In fact, that goes back to as early as the 1920s. For starting from the first time that the spinning detonation was discovered through imaging, what we see is in all cases, detonation wave does not like to stay in one dimension. You always see higher dimensional structures. So therefore, from the 1920s to close to the mid-70s to late 70s, quite a significant amount of work has been done in exploring the cellular structure of detonation. The result of this, the experimental work has led to a series of a cell model being developed, mostly by the Russian scientists and researchers at the time, and by others, specifically focusing on internal structure of a cell. And I will talk about the cells in more detail at a later time. Now, with the advance of high-speed diagnostics and imaging, after the, in the last 20 years, much of the study has been focused on the detailed structure of detonation wave front, for that how the shock wave propagate, how do they bifurcate, the wave speed, how the waves interact with each other, and how the interaction of the waves influence the chemistry, and the chemistry influence those waves, all become very interesting topics of this research field. So first thing, couple of things I wanted to just go over some of the basics, and this is how I learned detonation, starting from very simple experiment on using detonation tubes for the experiment. And we recorded the structure left over by the detonation wave front by a smoke foil method, and that's a traditional method. Now, I come from a background of chemistry. Therefore, the first thing that I like to look into is always chemistry. That gives me some comfort in the experiment results, in my ability to interpret it. So this is how I started. We took a hydrogen-oxygen mixture at a 15 kilopascal, reduced the pressure, mostly for safety reasons. We look at the cellular structure for that mixture. For 1D representation, you can look at the induction length here for this particular mixture, but more interesting to me is the question of, can we modify chemistry of the induction period and therefore altering the induction length without impacting gas dynamic properties like gamma? So for this experiment, we added 3,000 ppm of ozone, leading to reduction in the induction length. And surely enough, as understood from before, we see the cell size becomes about 1/2 of the case without ozone addition. So chemistry impact detonation, obviously, and this is not new. And if you look at the cell weights over a broad range of pressure, with ozone, without ozone, because of reduction in the induction length, we see that the cell weights also become smaller. Of course, detonation velocity, on the other hand, is a thermodynamic quantity. And we know that. And despite the cell structure difference, we do not see differences in detonation speed, wave speed. So this is an interesting aspect of this problem. So let me change this to a later point. Maybe we can see the cursor a little better. The addition of ozone, of course, upon heating quickly generated oxygen atom. Oxygen atom would react with H2, therefore jump-started the chain reaction process and chain branching, leading to fast ignition chemistry and therefore smaller cell size. Okay. Now, so the next question that we want to ask is cell size being impacted by chemistry? And later on, we will show that cell size is also impacted by other properties, mostly physical properties, for example, the specific heat ratio. Before I get there, let me discuss. While we have detonation cell structure, cell is ubiquitous to 3D detonation. So therefore, next question is, to me, is cell size a fundamental property of the mixture? So for that, we went back to look at the large range of literature. We consulted extensively with the database at Caltech by Joe Shepard. And so this is what we concluded. All right. So if you look at the various cell structure and size measurements in different geometry, in the case of a structure, it's a square, it's a rectangular duct. In our case, we have a tube. We actually have two different tubes. One is 32 millimeter, the other is somewhat smaller, 6 millimeter. And we were comparing things with everything else being equal with regard to the stoichiometric, with regard to the mixture we probed and the pressure and initial temperature. We'll compare the cell size and distribution. I'll just show you one example here. In rectangular channel versus a round tube, when we plot just one such size, cell size characterization, that's the cell aspect ratio. That's the length of the cell divided by the width of the cell. And plot as a function of a cell width, that's this quantity, we found that for a given pressure, or rather given initial condition, we see very wide range of variation. You can look at the cell aspect ratio, looking at the cell weights, or fixing the cell weights, look at the cell aspect ratio. They differ in both cases by as much as a factor of 2. So that led us to think that there are several things that's going on here. Number one is that the boundary conditions clearly impact cell size. In other words, the other way to look at this is cells and cell structure, cell size may not be a fundamental property of the mixture as it's impacted by how we conducted the experiment. The second thing we have to consider is smoke foil is not a direct measure of detonation wavefront. Smoke foil measures the shadow of the detonation wavefront. The very reason you have the cells as measured on a foil is because of the detonation wavefront interacting with the boundary condition or with the wall of detonation confinement. So to many people, this may be obvious. To me, it wasn't. So it was rather revealing. And of course, that leads to the subsequent work we start to think about then how do we understand this problem at a quantitative level? Okay. Now, just as a further illustration of the points I made, it's not just 2 measurements. We made a conclusion. We look at many measurements, and this is one example, all for stoichiometric hydrogen in oxygen with unburned gas temperature 300 Kelvin and 20 kilobar of unburned gas pressure. So if you look into this box, just zoom in, we look at a large range of measurements, all done on the same condition. And just take the limiting case example. If you do this in experiments in metallic tube with a diameter of 1.2 centimeter, and using glass plate insertion method for recording the cells, what you get is a cell width that's about 12 millimeter. And down below is the other experiment in rectangular channels and with dimensions that's specified here with cells recorded by Mylar sealing method. And then you get this cell width down below. So they differ by factor 2. And if you look our measurements using a tube at a 32 millimeter made of polycarbonate and or quartz tube, we tried both with plastic soot foil. What do we have is 9 millimeter. Okay. So the point here is that, again, those measurements shows that the cell width varies with the way how we measure them. Okay. Now, computationally, there are also evidence supporting the fact that the cell width is impacted, or cell size is impacted by the boundary condition. Depending on how you initialize a 2D direct numerical simulation, this simulation is done by Alexei Pulenenko at UConn. Depending on how you initialize it, you find that the channel using non-slip boundary condition can accommodate 1.5 cell in width, 2 cells, and n number of cells, depending on how you initialize it. And if you look at this problem, you realize that the wall and the boundary, in fact, modulating cellulose development, in that shock refraction of the wall is a key factor in controlling the cell development and the structure. Of course, this is a 2D numerical simulation. In 3D, things are very different. In 3D, we see lesser mode locking because you have a third dimension and you have more opportunities for the cells to relax to its preferred structure. So that said, if you ask me, what is a preferred structure? I do not know because, again, whether it's a 2D or 3D simulation, all of which are impacted by shock refraction of the wall. So, of course, in that regard, we also learned that the periodic boundary condition attempting to mimic detonation in infinite domain doesn't quite make sense just because you artificially induce mode locking at the boundary, but that's a side point. In 3D, in a square, when we do direct numerical simulation, again, this simulation used the code of Andrea Kemp from University of Duisburg, and looking at in the square channel, the propagation of detonation wave. And what you are seeing here, the video shows the pressure contour in the wavefront. So we're following the wavefront and looking at how shock waves propagate, intersect, and so on. So for square channels, you see very regular cell structures if you look at the front side. And then if you look at this in a comparable condition, if you go to a tube, you see similar structure in the wavefront qualitatively. Quantitatively, the cell size and the cell structure are quite different. Now, some of you who do this simulation would realize that those simulations are extremely computationally extensive because of 3D simulation with detailed chemistry. Now, a key point here is if you ask me whether this simulation had been fully numerically converged, I can't tell you. We cannot get to, we only have the necessary condition to show that the computation is likely to be converged, but there's no sufficient proof for it. We did do numerical resolution sensitivity study, at least to ensure that under comparable conditions, the conclusions we reached here are not impacted by grid resolution. The grid resolution here is 20 micron, and we've gone to as small as 5 micron in grid resolution. Okay, so the key point here is that depending on the confinement, the geometry of the confinement, you are going to get the wavefront propagation dynamics somewhat different, and that difference is revealed only to an extent by the smoke foil. For that, as I discussed earlier, smoke foil is nothing but a shadow of detonation wavefront. It isn't the detonation itself. So that said, let me move on and make a couple of comments summarizing this set of a simulation. First thing first, the 3D numerical simulations reveal the following features of wave propagation in channels of different geometry and shape. It's highly dependent on a boundary condition, obviously. The cell size appears to be a joint property of the mixture, the boundary condition, and possibly the initial condition of grid resolution even. The channel and the tube gave fairly different kernel structure. If you zoom in, look at the local thermodynamic state and how those states evolve temporally and spatially, you see quite different dynamics. So to that end, it is actually now surprising to me to see cellular structure as measured by smoke foil that are actually quite close to each other. So the other point I want to make is, while cell size is not solely a mixture property, the boundary condition effect is far smaller than turbulent combustion in many ways. As a matter of fact, as far as burning rate is concerned, so long as you stay away from the detonation limit, then you can get to the detonation limit by reducing the channel or tube diameter, channel size or tube diameter. As long as detonation wave is propagating close to the CJ speed, and it remains to be a thermodynamic quantity and not much details impacted, whether it's the cellular development or local pressure structures. At a detailed level, however, if you look at just, in a case of a channel simulation versus a tube simulation, you see local shock propagation dynamics within, for example, a detonation cell. Very different, starting from overdriven to that equal to CJ speed to overdriven. So locally, the structure and thermodynamic state evolution is highly dependent on the boundary condition. Okay, so now this is what get me into trouble. For years, I didn't know what to look at it. Is essentially that this observation calls into question of what we should be measuring, and how do we compare measured with simulation. So unfortunately, the implication here is that while we can compare simulation with measured detonation speed, but that since detonation speed is a thermodynamic quantity, as long as you have a robust detonation wave, you are not going to be able to learn much. As in terms of a detailed structure of detonation wave, this is a question that we cannot address just because we cannot compare measured to any simulation. In particular, it's because of those boundary condition impact becomes quite significant. And speaking about boundary condition, at this point, most of the simulation assumes you have a no-slip boundary condition, and then the question becomes how do you treat the heat loss, how you treat a variety of other effects, including the loss of energy through shock impact with the side wall. All are open questions at this point. So that said, it's not that we don't know. Many of the things we learned in the past are still applicable here. If you ask if you ask different questions. In terms of detonation wave regularity and irregularity, in detonation literature, often when you do a smoke foil measurement, when you see the cell structure to be, well, regular being they have periodicity as versus stochastic appearance of the detonation cells. You do see this, and this type of structure in case 5, where my cursor is typically called the stable detonation. When you go to case 7, and as measured, the detonation cells are exhibit a stochastic structure, and the literature often calls this unstable detonation. I like to call them regular versus irregular. Unstable implies that the wavefront propagation can be unstable, but there is no evidence indicating that when you have an irregular structure, the detonation wave is unstable, as a matter of fact. So this is something that I wanted to make a point. So from here on, regular versus irregular cells are mostly, in my mind, refers to the cell structure, and we should not infer this using the cell structure to infer stability of detonation wavefront. Mate, let's go have the, yes, please.
Could you please say that again?
So I assume this is a question coming from the audience. So between stable and unstable detonation versus a regular and irregular cell structure in detonation, there's a distinction between the two. A regular celled detonation wave versus an irregular celled detonation do not state anything about the stability of the detonation wavefront. Nature tends to chaos, nature tends to be irregular. So I would like to view, perhaps the best way to say it, is that when you have a regular celled detonation, as you observe, for example, through smoke foil, it is a special case of irregular cells. The difference is that local dynamics of gas dynamics, hydrodynamics, and chemical reaction behaviors may be different. I'll get into some of this issue a little later. It does not indicate, for example, if you compare case 7 to case 3, case 7 is less stable. Okay. So anyhow, so the question then, I do not know if it's my laptop doing this.
Something went wrong. Please try again.
Ah, okay. This is just the background somewhere. So anyhow, that said, there are still certain questions that can be asked, and the original idea came from Mate Radulescu's work concerning what factors govern the detonation wave in terms of a cellular structure, comparing regular versus irregular cells. So Mate pointed out that there are two factors we need to consider. You can have to look at the apparent activation energy of ignition. So that's the governs the induction length in the 1D sense. The second is a gas dynamic property, that is specific heat ratio, gamma, Cp over Cv, behind the shock or the von Neumann state. These two properties jointly impact the cell regularity. So it turns out that this is known from before. Regular cell comes from a small activation energy, but a large gamma. And irregular cell coincide with unburned mixture that has a large apparent activation energy to ignition, but a small gamma value. And with the ozone addition as a tool, we were able to isolate these two factors fairly cleanly, in that you can hold the activation, excuse me, if you look at case 3, 4, and 5. 3, 4, and 5. You can design the three mixtures such that apparent activation energy stays the same, but the specific heat differ. And this is achieved through adding ozone, modulating the apparent activation energy through ozone addition. And indeed, as you increase the specific heat ratio from around 1.25 to 1.43, 1.44, you see the cell becomes more regular. The other direction is if you move in the vertical direction of looking at case 3, 6, and 7. And these are the mixture with mixture conditions correspond to a fixed specific heat ratio, but increased apparent activation energy. Under that condition, the higher the activation energy you see, the more irregular the cell becomes. In other words, the longer for us to go to ignition, the more likely the cell will go irregular. And now we're still working on this problem. I think we have a hypothesis as to why this is so, but this problem cannot be entirely just looked at as already illustrated. It's also dependent on specific heat. So what about a specific heat ratio? How does that impact certain features of detonation? And that's something I wanted to perhaps address. And I wanted to address this issue by looking inside of a detonation cell. And more specifically, the evolution from overdriven to underdriven wave speed within a cell. Again, this phenomenon is known for a very long time, and actually it is one of the most important quantitative finding concerning detonation wave and detonation wave structure, in my view. A paper by Crocker in 1969 measured the shock wave speed within the cell. So if you follow from the birth of the cell to the death of the cell, moving along this dashed line, and that's what this x-axis, we call this cell position. And there is an incident shock moving from left to right, from the birth of the cell to the death of the cell. And plot this quantity relative to the Cj speed, the thermodynamic quantity of the mixture. And for many experiments, it can be shown that initially at the birth of the cell, the wave is overdriven with respect to Cj speed. After we pass about this point, middle of the cell or 1/3 of the cell, this wave becomes underdriven. That is, the shock wave speed becomes smaller than the Cj speed. And you can look at other experiments, all showing the same thing. If you look at the cell of hydrogen, oxygen, argon detonation, starting from the birth of the cell to the death of a single cell. You start overdriven by looking at the D over dCj ratio. 1 is the Cj speed. You start overdriven, then to underdriven. So why things happen that way? The hand-waving argument is quite simple, but this requires validation. That is, if the overall mean speed of the detonation wavefront is thermodynamic, as is determined by Cj speed, for the time being, let's not worry about the velocity deficit, and those deficits are usually due to losses or some kind of loss, whether it's a heat or momentum loss as you propagate detonation wave. So if you focus on this profile, a quick argument one can make is why the system detonation wave does this is simply because in order to maintain an average detonation speed as given by dCj, the Cj speed, locally and occasionally, you must overdrive it. And this overdrivenness ensures that you will reach or have the necessary condition to achieve a mean speed that is equal to Cj speed. Because if you do not, any perturbation will cause the decoupling of the wavefront from the heat release. And as a result of it, you will not get a stable detonation. So in other words, this is what I said here is not new. This is all understood. That is, you have to overdrive it in order to achieve a mean speed that's thermodynamic. So that's very interesting to me. And if you look at the detailed structure of the cell, there are several features. You have at the birth of the cell to the death of a cell. And these 2 points is related to the neighboring cell. And I shall leave them on the side for the time being. And you have a triple point. That's because of collision of 2 sets of incident shock. Within a cell, I have 1 shock. So therefore, I have a neighboring cell. And this neighboring cell is also running a shock. So I have an interface between the 2 shocks. And this generated a triple point, and you can follow the triple point trace, and that is, in fact, what the cell through the smoke foil will record. Historically, there are several explanations as to why the triple point is capable of carve a line into the soot foil, and one most reasonable explanations relate to something I will say later is vorticity generated, rather intense vorticity generated along the slip line. But let's focus on the cell now. We have a shock heat up the mixture behind it, and there's an ignition delay involved. So reaction heat release occurs a little later. Because this shock is diverging, in other words, you are propagating a shock from a small area to a large area. Shock must reduce its speed initially, at least initially. Since the reaction front is behind, it, strictly speaking, does not necessarily have a mechanism to feed the energy into the shock. So in fact, historically, how the energy release and the shock front is coupled remains to be a question. I'll come to this issue a little later. Then pass through the midpoint of the cell, shock continue to propagate, although it's slowed down. And because now shock is slower, less intense, causing less amount of compression for the gas behind it, so the ignition delay becomes longer. That's represented by the distance here. So as a result of it, you see larger and larger spatial spacing between the shock and reaction front. So you can trace the shock and you can trace the front of the reaction, and then you'll see the distance will become longer. And at the death of the cell, you have now a pocket of unburned gas, obviously, and I'll talk about this pocket of unburned gas a little later. So by studying this detailed structure, some of the things we can learn is overdriven to overdriven dynamics is necessary to maintain a constant Cj speed. And now let me talk about specifically I'm using perhaps more time than I should, so I need to speed up a little. So let me talk about the historical blast theory. Okay, historically, to explain the birth of a new cell, it relies on the knowledge of about this unburned, what is often called a keystone pocket of unburned gas. It is said that with this unburned pocket, you have the pocket being heated by the incident shock and subsequently by the transverse shock wave. As a result of it, you have a very hot pocket of unburned gas and it explodes. When it explodes, it generates a shock running in, otherwise called a Mach stem, being propagated in from now at the depth of the cell, generating a new cell. And it's a compression wave. What is strange with this explanation is that if it is a blast wave, then we expect this wave to be isotropic. Therefore, we should see wave appearance in a direction perpendicular to the shock front. The shock will, the detonation propagated from left to right. And those are the two neighboring cells. You should see shocks coming into the neighboring cell to an extent. And the fact is we actually don't see it. So this led me to think that something must be different from this historical blast theory. And what's related to this is I didn't understand why and how is the blast energy transferred preferentially into the unburned gas. And it causes overdrivenness, so there must be quite a bit of energy dumped into the new cell as the new cell form. So what's the mechanism behind it? And it was the role of the neighboring cells, because if you look at detonation wave, if you focus on the cell, it must talk and interacting with the neighboring cell here. Okay, so this is something I want to quickly address. So I was on a sabbatical at Duisburg, happened to have an office next to Andrea Kempf. And he and I start to talk about detonation, so he even moved forward with some preliminary simulation. And one morning he jumped into my office and said, hi, something I want to show you. That is this structure here. Now this structure coincides with the birth of a new cell, or rather the very early stage of a new cell. What you see here is you have a frontal shock. You see some indication of a Mach bifurcation. And more importantly, you see the vorticity, and you see something that's in the middle. And if you look at this whole thing, you say, this picture isn't as clear. That is, if you have a pair of vortex in a 2D or vortex ring in 3D. If it's a donut, if the donut center collapse, this is essentially going to generate a jet. And this structure looks like a jet somewhere. So Andrea got very excited to say, what does that jet do, if there is one? So that question kind of inspired me to look into this problem a little further. So I came back to the States. I tried to put a couple of things together and started looking at this problem. That is, A is vorticity. Vorticity will lead to jetting, will lead to Mach stem bifurcation. And then is that a mechanism for energy focusing? If energy is being focused, where does that energy come from? This is what I wanted to briefly discuss next. So I came back to the States and talked to Alexei Prudnenko. And running a set of simulation by Xinyu Zhao's student Patrick Meager. And this is what I wanted to show you on this chart. Everything is pretty much summarized on this chart. Okay. On the top, it's a video showing gas particle velocity U normalized by instantaneous Mach stem speed. So the Mach stem speed, keep in mind, this Mach stem speed is basically overdriven wave speed within the cell. Gas particle velocity is I want to show you that there's a gas jet immediately following that Mach stem. And the jet lasts for a long time. And that is a mechanism for overdriven wave production, sustaining it, preventing it from decay due to diverging shock. And if I have a gas jet, then I must have localized the kinetic energy. This kinetic energy, if I combine this with chemical and sensible enthalpy, I wanted to look at the total enthalpy spatially and following the evolution of this total enthalpy to see how energy gets concentrated. So the color scheme here on the top, anything above 0, this is actually should be U minus D divided by D minus 1, forgive me for the typo. So anything larger than 0 shows that you have a gas jet velocity higher than the wavefront velocity. Okay. And again, the warm color indicating energy that get concentrated exceeding that of the CJ kinetic energy. Well, this is a movie, so let me just play it. Okay, let me stop at this point. How do I stop it? All right, so we'll let it finish and we'll play this again. And while we play this again, I can tell the story why it's moving. And while we're doing this, some of you might ask me, why did we add CO2? The reason we add CO2 is we want to amplify an effect that I wanted to discuss here. That is, the jetting behavior is becomes more important when you have a small gamma value. Later on, I'll show you with a high gamma mixture, it's the same thing. Now, I wanted to. Okay, this is better. So at this point, a new cell form, and you see this jet. This jet is measured by jet speed, and its magnitude is higher than the Mach stand speed. So what you see here is that this jet is what's continuous. It's a supersonic jet, continue to support the wavefront and providing energy to it. And therefore, if you, again, let me go back. And then if you look at the total enthalpy, now focusing at this point, now you start to see the most of the energy gets concentrated where the jet is. So the jet is what the energy focusing mechanism. So the next question, I will now talk about this chart, but the next question is, how does jet form? And this jet form is best represented by this image, a snapshot at a -75 nanosecond to the time when the new cell form, okay, or rather the triple point collision point. There's some ambiguity. Triple point collision is never a collision point. It is a rather spatial region, but that said, it's not as important. What you see here is that at the end of the cell life, you have a neighboring cell. This is incident shock. And then you have a decaying shock so slow that trailing behind it. So right before the cell is death, you have two shock intersection, or rather this shock intersect the incident then shock intersect another incident shock in a neighboring cell. That you have a very strong slip line. There's a lot of torque resulting from a strong shock and a weak shock. So this is a vorticity plot showing a set of vorticity on the top and a set of vorticity on the bottom. Now, the vortex has not collapsed until a new cell is born. And right after the new cell is born, precisely in this case, 75 nanoseconds following the triple point collision, you see this pair of vortices collapse onto each other. And this in fluid dynamics is all well understood. Then when this happens, it generates a jet right in the middle. And it is this mechanism that leads to, if you look at the total enthalpy, a focusing mechanism, right at the birth of the cell, and moreover, continuing in a very early life of this new cell. So in summary, vorticity generated along the slip line and the collapse of the vortices led to a jetting. Jetting is what's responsible for production of the overdriven wave and energy focusing, leading to the birth of a new cell. So then if you ask the question, where does this energy come from? In fact, this energy comes from the two neighboring cells. Okay, I'll come to this point a little later. In the interest of time, I will just skip this chart. So we did some more work on it and try to understand how does jet turn its energy into the shock. And this, in fact, is just essentially a virtual piston effect. Because I have a jet, I'm pushing the shock in front of me, and behind the frontal shock, I have gas coming in through the shock, and behind it, I have a jet, and therefore I produce a contact surface. The contact surface is the point at which I should have highest pressure. So if you look at the DNS simulation, this is the result of DNS simulation of one cell. You see that the pressure is the highest, not at the shock, right behind the shock. In fact, there is a spatial distance for which the pressure reaches maximum. And the jet, of course, is what's responsible for it. And it is through this mechanism that jet keeps the reaction occurring behind the shock close to the shock. And that further strengthens the shock and sustains the shock, keeping the overdriven for a much longer distance than otherwise you would be able to achieve, because that diverging shock through area expansion should decay much quicker than anything that we've measured. I talked about it earlier about a funny mixture. Now let me remove CO2. So this is a high gamma mixture, and the high gamma mixture does the same thing. Let me play this image. Burst of a cell, and you see a jet still smaller in size and perhaps lower in intensity. Nevertheless, a jet and total energy focusing due to the kinetic energy of the jet. Okay, so we think this conclusion should be quite general. We're still looking at other mixture to see if there's anything we've been missing. So again, just this chart summarizes what I want to say, and that is you have a shear layer as a result of the collision, or rather the intersection of two shocks. And the marks then interact with the instant shock in a neighboring cell, producing a shear layer, and that shear layer generates vorticity. That vorticity forms a vortex ring, and obviously it becomes evident by angular momentum conservation. Globally, you will get cell just because as much as you have a vortex ring on the top generating from the shear layer on the top, you would have likewise for regular cells generating a vortex ring of overall globally all add together same angular momentum or zero angular momentum, and that leads to forward jetting and regularity of the cell. Of course, the forward jet, by momentum conservation, must produce a real-world jet. And this real-world jet, keep in mind that behind it, I have the old cell, and I have that pocket of unburned gas. In fact, it is this real-world jet that finish the reaction in that you have the pocket of gas compressed by a very weak shock first, then by the transverse wave, and then lastly by the real jet, real-world jet. And that real-world jet causes ignition behind it that provide a pressure wall behind it. And that causes the most of the energy being focused and transport to the front. So as much as you have this forward jet, you must have this backward jet in order to balance that momentum. So this is the reason why majority of energy gets transported to the unburned gas, and that leads to overdrivenness and so So in a way, fundamental fluid mechanical principle is well known. It's even people sell this kind of thing called a vortex cannon or vortex gun on Amazon. That is through vortex, you can generate a jet. Conversely, if you have a jet, you will have a vortex ring on the base of this jet. So this is not something we invent. It's all fairly well understood. All right, so the interesting time, I probably will skip through the next part is to explain why we see regular cell structures and what is the feedback mechanism. And but this is a rather minor point because we only have half of the story. We explained that why cells are regular, as shown here. But we're still working on what is responsible for irregular cells. So all that said, let me just summarize everything that I said in one chart. If you look at a detonation wave, I like to view detonations as autonomously propagating energy centers. And the centers have structures. And these energy centers are sometimes called hotspot. And this hotspot is due to interplay of gas dynamics and chemical reactions. And hotspots are basically responsible for replicating cellular structure. So in my mind, what is more important to look at in moving forward in this science of detonation is about hotspot. It isn't about the cell. Cell is only in a shadow of the traces, those hotspots, if you will. So the local energy structure death of a previous cell produces a new structure leading to birth of a new cell, and that's quite obvious. And as far as the cell life is concerned, from birth, early life, midlife, late to the death, each has its own interesting energy transfer mechanism. And most importantly, at the birth of the cell, the dynamics and energy momentum transfer is governed largely by microscopic hypersonic jets. And hypersonic jets is produced by vorticity. So I used to think that most of the energy of a new cell, I call this a daughter cell, comes from the cell behind it. But by understanding, looking at the detailed structure of the direct numerical simulation, it becomes apparent to me that the initial energy transferred into the new cell responsible for Mark-Stem bifurcation overdriven wave comes mostly from the two neighboring cells, or what I call the mother cell. And this two parent cell gives rise to the new cell. But the older cell, what I like to call the grandma cell, its residual energy in this unbound pocket is important in that the backward jet, in order to conserve the total momentum for the gas jet moving forward, produces intense chemical reaction and therefore a pressure wall that's provided a sufficient condition for most of the energy being moved to the front. So it's an interplay between momentum and kinetic energy in many ways. So this is how I view now the new cell genealogy that is different from the blast theory. Top level summary, quasi-1D detonation wave always choose to bifurcate its essential quantity spatially, and it finds a mechanism by which you can concentrate energy or generating hotspots, or what I call APEX, autonomously propagating energy centers, and that propagation preferentially is in the forward wave direction towards the unbound gas. Okay. Early cell dynamics controlled by a continuous process of extracting energy from the neighboring cell or the mother cells around the triple point line, and local overdriven wave produced from jetting leads to gas compression. Is a process by which you have a compression, jetting, further compression through a virtual piston effect, leading to the overdriven shock in a new cell. And hotspots or apex generation is essential to gas wave detonation. And that is something I very much like to focus on, as that it provides the key for us to understand energy transfer from burnt to unburned gas in detonation. So I'll skip this slide. But let me just summarize conclude this talk. Sorry, I ran it perhaps a little longer than I should. So this is my last slide. So outline some of my thoughts about the challenges and opportunities with respect to gas detonation, and for that matter, multi-phase detonation. Challenges and opportunities. Fundamental aspect of the problem, I think there are two. The first is, if detonation size parameters are not fundamental mixture properties, then what properties or measurements of detonation wave we should be looking at it? Now, this is not a new question, not a new idea. Many people before me, Joe Shepard, Mate Redlesko, John Lee, and many others have attempted over the past 2 decades trying to find new measurements to enable better theoretical understanding. That said, I think there is still need for new low-dimensional, well-defined experimental concept, new ideas for diagnostics. So in a way, if you mirror between detonation and turbulent combustion, a low-dimensional canonical experiment that one can do and tackle and compare experiment with theory is that of a laminar flame, whether it's stretched or unstretched. So the connectivity between turbulent flame, a more complex problem, versus a more defined problem with laminar flame, that analog is currently missing in detonation. We do need to find this well-defined experiment configuration or set of this configuration to enable us to better understand detonation. Global detonation wave comparison is unattainable, simply because it's highly boundary condition dependent. And of course, this should inspire new diagnostics. The second implication for what I learned in this process is, if overdriven wave is driven by supersonic jetting, then the energy transfer process and the consequence of this energy transfer process, whether it's a gas dynamic behavior or kinetics, occur under non-equilibrium condition. So therefore, the opportunities to us is questions we can ask are, what is the role of thermal non-equilibrium on gas dynamics and reaction kinetics? And currently, in fact, it's a leap of faith for us to use any of the reaction mechanisms and models we and the community develop, apply to detonation. For that, usually, in detonation wave, the kinetics occur in a non-equilibrium condition and ultra short time scale, as short as 100 nanoseconds. So that region, we've never had any experiments that enable us to test, validate those kinetic mechanisms. And of course, you can equally argue that is the Navier-Stokes equation is still valid for this problem, and how valid can it get away with it, and so on. Okay, so as I'm a chemist, I'll try to focus on chemistry problems rather than gas dynamics. So please feel free to add at the end of this talk what other problem that may be causing given this understanding. The practical aspect of the problem is this. Okay. If detonation wave is now driven by microscopic hot spots and jetting, from engineering point of view, could the vorticity and the hot spots be engineered? Can you engineer them such that the feature size becomes substantially smaller than natural gaseous detonation? These cells are typically of the order of a centimeter to a decameter. Can you engineer hot spots at a micron size? If so, can we achieve pseudo one-dimensional detonation? And if you can achieve pseudo one-dimensional detonation, then this will help us to solve many of the structural dependent engineering problems as in, for example, rotating detonation engine. As important, I always say that even though detonation is sensitive to chemistry, detonation still offers a significant opportunity for us to develop energy conversion methods that is not so much field dependent. And that is, but to do so, we need to engineer those hot spots, ensuring heat release occur behind the detonation wave front fast enough such that the global burned gas is choked. So this concludes my talk.